Okay, so hi everyone, I'm Pierre, and today I'm gonna tell you about, no, it's going alone. Okay, I'm gonna tell you about a LightCon approach to compute cosmological observables beyond the unordering perturbation theory, a project done with Giuseppe Fanizza, Giovanni Marozzi, and Mateusz Medeiros. So to give you the general motivation for this work, we know that, as Mario recalled so far, we are about to receive an unprecedented amount of high-precision data from large-scale cosmological surveys. And so to take advantage of these new opportunities, our theoretical predictions should be as accurate as the level of precision set by cosmic surveys. So this means that we have to include nonlinear effects in our formula because they will have physical an impact on large-scale structure cosmological observables. And to do that, it can be convenient to use these so-called geodesy LightCon coordinates, which account for how light rays propagate in a clumpy universe. And we know that they do that on the past LightCon of a given observer. So to give you the main idea of what's going on, suppose that you are at the sea and you would like to measure the position of a fish in the water. And we know that because of refraction effects, the real position occupied by your fish, your source, is going to differ from the measured position, the one that you can infer from your observations. And this is because in general we don't use a frame of coordinates which is adapted to how light rays propagate. And if instead you use GLC, you incorporate in some way all the information about distortions directly into the geometrical formalism you use to describe your spacetime. And so this enables you to get the most important, one of the key requirements about this set of coordinates, which is that the angles, so you suppose you parameterize the positions of the source in terms of two angles in the sky, as usual. So what happens is that the angles you measure will exactly be equal to the real angles of your source. And as for the other two coordinates, we have that tau is a time-lag coordinate selecting a free-falling observer, and W selects the past LightCon associated with this observer. And then it turns out that the only metric which is compatible with these requirements is this metric here, which has a fully nonlinear behavior. And what's nice about GLC is that in this gauge, observables have fully nonlinear expressions. For example, for the redshift, the galaxy number counts, the angular diameter distance, and the redshift drift I'm currently working on. And then you can build a perturbation theory directly on the LightCon of this observer. And what's nice is that observables are just expressed as products of local perturbations, just evaluated at the source and observer position. So the results I got are in general gauge invariant expressions for cosmological observables to higher order in perturbation theory. And in the specific case of that paper, we focused on the angular distance redshift relation, providing the kind of ultimate formula gauge invariant as seen by a free-falling observer and with new terms at the observer position accounting for this gauge, for this observational gauge. And this is also a way of eliminating divergences around the observer position. And you can do that in a model-independent approach. So thank you, and feel free to ask questions later.
Thank you. Michele Benacco.
Hello everyone, I'm Michele, and I will briefly talk about stochastic gravitational wave from modulated reheating. Now, what we basically did was to investigate small-scale primordial perturbation sourced by an X-like spectator field. You can see our Lagrangian. We have phi the inflaton, chi the spectator, which has a non-minimal coupling to the Ricci scalar, and an X-like self-quartic coupling. We applied the modulated reheating, which basically means that the decay rate of the inflaton depends on chi. So spatial variation of chi means spatial variation of gamma. So different region of the universe will experience a slightly different reheating history. We have considered two possible setups in which the inflaton can decay into vector or fermions with masses that are set by the gauge and Yukawa coupling with the spectator. This was the setup. Then we applied the delta n formalism to compute the curvature perturbation. The important things here is that in our setup, zeta split in two, and the contribution from the spectator is intrinsically non-Gaussian. That said, we applied the stochastic formalism and a spectral expansion, And this leads us to blue tilted power spectra, as you can see on the right. Now, at second order, curvature perturbation acts as a source for tensor modes. You can see in the plot omega, gravitational wave spectral densities, as a function of the frequency. The different colored lines are the sensitivity curves, while the black lines are the signal in this setup. Here is basically our main results, which show omega, so the signal at a given frequency, which is the minimum of one of the sensitivity curves, as a function of the non-minimal coupling and the Yukawa coupling or gauge coupling for the two different channels. What we can see here is that the signal can reach the sensitivity of future experiment, in particular BBO and the SIGO, the colored dashed lines, but only for large value of the Yukawa and gauge coupling. You can see the standard model values with the white lines on the bottom. Now, this outcome basically comes from a non-trivial interplay where the Planck non-Gaussianity bounds strongly constrained the large-scale power spectra. Then I finished. If you want to know more about this setup, please come to visit my poster. Thank you.
Thank you. So next we have Dibya Chakraborty. Here it is. You have the floor.
Hello, everyone. First of all, I'd like to thank the organizers for this opportunity. I'm Dibya from IIT Madras. And as the title suggests, I'm going to bring in string theory. So string theory, where the fundamental blocks of string theory are the tiny vibrating strings, which are of two types, open and closed types. And in order to connect to the four-dimensional physics, where I'm going to study or I'm going to present inflationary models, I'm going to dimensionally reduce this extra. So the string theory I'll be interested in are these 10-dimensional type 2B superstring theory, where in order to connect to the 4D, I'm going to dimensionally reduce the extra 6 spatial dimension. And the information will not be lost. The information will be there in the internal manifold where I'm going to compactify, which means that I'm going to get rid of this extra dimension, and which will be for phenomenological purposes will be this Calabi-Yau manifold. And the Calabi-Yau, from this Calabi-Yau manifold, because it contains all the information of the extra dimension, the Lagrangian that I'm going to write, which contains the potential energy and the kinetic energy, that potential energy which will help us to drive inflation is going to have an origin from string theory, as well as the scalar fields driving inflation. I'm going to try to find an origin to that from string theory. And in order to just to crudely show you what are the scalar fields that are going to drive this accelerated expansion, so they can be from this extra dimension, they can be related to the topology and shape, or they can also be the extended objects like deep brains. So for my purpose, my scalar fields will be the shape of the extra dimension. And the models that I'm going to show you in my talk is that they are from the setup that I'm going to consider is a perturbative large volume setup. So if you are familiar with the KKLT and LVS, I can explain more if you come to my poster. So this perturbative large volume scenario is an improvement to this KKLT and LVS because it does not exploit any non-perturbative effects. And the scalar field in this case is the whole, so this full 6-dimensional volume. And the upshot of this scenario is that it is a small field inflation, which means it is in compliance with the de Sitter-Swampland conjectures. And the next model that I'm going to show is again a single field model. So it is a fiber inflation, but in perturbative large volume setup again. And the fiber, this 4-dimensional manifold is my scalar field in this case. And again, the upshot of this model is that there is no bound on the scalar field excursion. The previous fiber inflationary model studied in the literature, they had this problem. So we were able to alleviate it with the help of our perturbative large volume setup. So if you visit my poster, I can explain more, and please come to my poster. Thank you.
Thank you. So next is Diego Cruces. Yeah.
Thank you. So, oops.
Yes, you have the floor.
Oh, okay. Basically in these 3 minutes, I will try to convince you why stochastic inflation is non-Markovian by definition, in case you don't know it. But and then if you want to know how we are trying to deal with the non-Markovianity effects, please come to my poster. So basically, how does stochastic inflation works, right? So we have a Hubble patch and some fluctuation, which is defined in the interior of this Hubble patch. And this fluctuation, of course, will go out, this Hubble patch. You can see in the bottom how it would evolve as sub-horizon scales. And then at some point, it will reach a wavelength which is large compared with the Hubble patch. And at this moment is when we will be able to start using the separate universe approach, okay? And this wavelength that evolved until some scale, which I call the coarse-grained scale, defined by sigma, when the small scale fluctuation reaches this wavelength, it will define a new background, okay? And this background will evolve following the separate universe approach. Now, we can do the same with a second fluctuation, okay? It will start evolving as sub-horizon scales in the fiducial background, in the white one, let's say. But then, when it exceeds this, the horizon, there will be some period of time in which this red fluctuation will evolve over the blue background, which is the background that is defined by the previous fluctuation. So this is basically the nature of the non-Markovian nature of stochastic inflation. Okay. So as you can see here, from N2 to N1 to N2, the red fluctuation is evolving over a blue modified background. This means that we have some memory of what happened with the previous fluctuation, and this is why the new background that we define is a mixture between red and blue, and this is why I try to plot it as a purple background. Okay. So in my poster or in this project, we are trying to model these non-Markovian effects analytically and see if they are important, if they are not. So please, if you are interested, come to my poster. Thank you.
Thank you. Yeah, the microphone. Yes, so next is Erika Florio. Thank you.
Hi, everyone. I'm Erica, a final year PhD student at Cambridge, and here I will present the results of my most recent publication. Now, the name of the game here is to initialize a stochastic gravitational wave background within a numerical relativity simulation, and to see if evolving these gravitational waves with full NR induces some kind of non-Gaussianity in the final signal that we recover. So we started off by making a mapping between the perturbative metric FLRW with tensor perturbation in, and the fully relativistic variables, which we evolve on our computer, which is this gamma and the k here. This mapping will allow us to do our initialization and also to extract variables in the linear regime. Now, the main issue with the initialization is these tensor perturbations, Hij. We can treat the polarizations of Hij as two separate massless scalar fields, and in this way, initialize it in the way we typically do for fields in lattice cosmology. Since we care in this work about near-horizon dynamics, we choose a power spectrum, which is the de Sitter approximation to the Mikhanov-Sasaki equation, which I've shown here. And this is the functional form we have on the first slice. Now, one of the main upshots of our work is that we found the phase, which is present in this linear solution, is in fact important in the dynamics, so one must include it on the initial slice if you want to recover the full evolution of the power spectrum at each k that you see. We then did a little bit more work on higher order statistics in the paper, but I'll leave that aside for now. If you want to hear more, come to my poster. I'll just lead with a short look to the future where we are looking to combine our code, which studies solely tensors, with the work of Johan Launi, who presented yesterday, in order to look at scalar tensor mixing into the future. So that's my work. Thank you.
Thank you very much. Yes, so now we have Juan Pablo, I forgot the last name, Garces. Okay, you have the floor. Yes, you can change with your hours.
Okay, hello everyone. So my poster is based on a project that we call Primordial Dirac Leptogenesis, together with Akil Ahmed and my supervisor Manfred Lidna. And the motivation of our project was twofold. On the one hand, we know that the standard model of particle physics has a lot of shortcomings, one of them being the fact that we observe a Barnard symmetry of the universe that is about 10 orders of magnitude larger than what the standard model predicts, and this of course motivates the search for new physics. And then on the other hand, we also know that lambda CDM without inflation requires highly fine-tuned initial conditions to agree with observations, and this of course motivates an early period of inflation. So what we wanted to do is to kill two birds with one stone, or actually two balloons, because ChatGPT was reluctant to give us a cartoon where animals are being harmed. But yeah, the idea was to study baryogenesis in the context of inflation. And of course, we're not the first people to ask this question. But in the context of neutrino mass generation, this question was mostly phrased in the context of Majorana leptogenesis, where you have heavy right-handed neutrinos that decay into standard model leptons and Higgs bosons. And via the interference of these diagrams, you get first an injection of lepton asymmetry that is converted into a Barnard symmetry via Weeks-Falleron processes. In our project, we were actually interested in an alternative leptogenesis mechanism called Dirac leptogenesis, where, as you can guess, neutrinos are of Dirac type, so lepton number here can remain unbroken. And even though the diagrams are not so different, the fundamental principle is actually vastly different. So what one needs here is a sequester, or what's called a sequestering mechanism. So one needs a reservoir of particles, in this case the right-handed neutrinos, that store lepton symmetry long enough to avoid the Falleron washout. Anyways, what's important is that in Dirac leptogenesis, the asymmetry production, so what's here in the green arrow, remains unspecified. And what we propose in this project is that this could be tied to inflationary dynamics, or more specifically, it could be coming from CP violating inflaton decays. So I'll just quickly flash here one example of our results. And as you can see, we have the inflaton field oscillating, and this induces a Barnard symmetry, as you can see in the dashed blue line. Yeah, any further details we can discuss together by my poster, and also some other things that we are planning to do next. So thanks a lot.
Thank you very much. So next is Yukiori. Sorry. Oops. Yes, so first is Raghavendra. Yes. Thank you. Oops.
Hello, I'm Raghavendra, a postdoc from University of Padua. This is a highly condensed slide of my work, which I did with Professor Nicola Bartolo, which is available at this archive identifier at the bottom. Basically, we asked the simple question of whether scalar-induced gravitational wave can serve as a probe of primordial parity violation, and we just demonstrate how it indeed can. Scalar-induced tensors are proportional to quadratic powers of scalar perturbations R, and so the 2-point correlations of scalar-induced tensors are proportional to 4-point functions of scalar perturbations. So the PHI, what I denote as PHI, is the spectral density of the intensity of these gravitational waves, can contain contributions both from products of power spectra and the trispectrum, the intrinsic, the disconnected and connected parts of the 4-point function, whereas the V mode, the degree of circular polarization of these gravitational waves, shall be directly proportional to just the parity violating connected part of the scalar perturbation, the 4-point function of the scalar perturbation. So the degree of chirality, pi k, the ratio of PHV to PHI, shall be proportional to T odd to P squared plus T even. Stokes inequality dictates that pi k should be of the range -1 to +1. If we substitute a simple form of trispectrum, the motivated forms of trispectrum, which are already available in the literature arising from semi-numerical computations of various models of parity violation, as is been parameterized by GNL and GNL tilde respectively, we get, once we perform the computation of PHV and PHI, we get the pi k, limit on pi k translating to GNL tilde being lesser than or equal to AS inverse, AS being the scale invariant power spectrum that has been assumed for simplicity for the first case. It is not so much of a great bound over large scales, but over small scales, if AS is very large, this can be a tighter bound. If we substitute a more phenomenologically motivated model of peaked scalar power spectrum, then we enter in, we see some interesting dynamics, particularly in a regime close to the peak where the chirality can be as large as 1 to 100%. There is a tail region where chirality can be 100% and is directly proportional to the contributions arising from primordial scalar non-Gaussianity, unscreened by Gaussian contributions, and all of these large degree of chirality is achieved just with representative values of GNL and GNL tilde to be 1. Just to emphasize that this is not a parametric form-dependent result, we also extended the form of trispectrum assumed with throwing in some intrinsic scale dependence of having an intrinsic peak in the trispectrum. We still recover the same dynamical behavior of a tussle or an interplay between the Gaussian and non-Gaussian contributions contributing to various degrees of chirality close to the peak of the scalar-induced gravitational waves spectral densities. So to more about it, please visit my poster, and I hope to see you more there. Thanks.
Thanks. Next will be Yuki Ori. It is. Okay. You have the floor for, yes, you have the floor for the 3 minutes. Thanks.
Hello everyone, I am Yuki Hori from Rikkyo University in Japan. This is ongoing work with Tomoaki Murata and Tsutomu Kobayashi. I'll talk about essential ingredients for chiral gravitational waves from two-form fields. Gravitational parity vibration may be observable through CMB polarization. However, the physical origin of such parity vibration remains poorly understood. One possible candidate is a non-minimal coupling between a two-form field, its dual, and curvature. Motivated by this, we consider a Lagrangian density that includes all dimension 4 operators constructed from these operators. In general, such a system exhibits ghost degrees of freedom. In this study, we investigate which Lagrangian densities are permissible in order to avoid these ghosts and whether chiral gravitational waves arise. First, we construct a dimension 4 action from a two-form field, its dual, and the Riemann tensor. This action contains ghost degrees of freedom, so we must impose constraints on its coefficients to eliminate them. After an appropriate field redefinition, the action can be brought into the same form as that studied by Lavinia Heisenberg and Georg Twinkler in 2020. However, this form of the action is still incompatible with isotropy, which motivates us to introduce a triplet of two-form fields. With this modification, the resulting energy momentum tensor becomes diagonal. Next, let us consider tensor perturbations. Tensor perturbations must satisfy both the ghost-free condition and the real propagation speed condition. These conditions can be expressed by requiring that u is larger than 0 and 2 beta h dot, where u is given by this expression. Furthermore, there is a possibility that chiral gravitational waves may arise. Extracting the parity vibrating term from the action, we find out that chiral gravitational waves are generated if the potential depends on y, where y is the contraction of the two-form field with its dual. In such a case, phi e and the zero component of the two-form field does not vanish. I'm looking forward to talking with you. Thank you so much.
Yes, so next person. Yes, okay.
Okay, so thank you for the chance to present my work here in this nice event. My name is João Santos, I'm from Brazil, and now I'm based here in the Germany as a Humboldt Fellow for 1 year. So in this work, me and my collaborators, we present this theory of gravity where we coupled the FRT gravity with time-dependent cosmological constant. And our goals was to find an analytic model and also to test this against the last set of Planck data. So here is the action and the Lagrangian of this one-dimensional scalar field. So the time dependence is going to be embedded inside of this scalar field. And here, for simplicity, I'm showing an example where we tackle the problem with GR in the gravitational sector and with a linear component of T, which is the trace of the energy momentum tensor. But we can generalize the method to other theories of gravity. So we're able to write the Friedmann equations and also to solve them. And we find some analytic models that we tested against the last data set from Planck. And we use the data set to constrain some of the free parameters that appear in the process of finding the solutions for these Friedmann equations. So these parameters here were the spectral index and the tensor to scalar ratio. And then the colored regions there are the valid values of our free parameters. And these rectangular regions, transparent regions, are the constraints imposed by Planck. So you can see that we can have some interesting scenarios where the models are valid. Beside this, I also would like to show you a project that we are developing there in Brazil, which is a radio telescope that we are building in the northeast of the country called Bingo. So we are building this telescope in this region here in the state of Paraíba. And the telescope has been built in the outback of this state. The final version of the telescope is going to be like this. So we expect to measure as our main scientific goal BAOs from redshift range between 0.13 and 0.48. And we are in the final phase of the construction. So I have some pictures here of the site of the radio telescopes, the structures to support the mirrors, and also the receptors. So we hope to get everything set until the end of the next year. So merci, thank you so much. It's a pleasure to be here. Thank you for the opportunity.
Thank you. The next is Shang Kong. Okay, you have the floor, Shang Kong.
Thank you. Hi, everyone. My name is Yanzong Luo, and today I am going to talk about entanglement evolution in slow versus ultra-slow inflation. And this is the work in collaboration with Sudo, Jaime, and David, and the ongoing work afterwards. So the ultra-slow is a special solution of inflation background, has the slow parameter such that the small scales got amplified, and it's a model. It's a potential mechanism for the primordial black holes. We are going to investigate the impact of ultra-slow phase in the entanglement structure of curvature perturbation using the OpenEFT method. And this is a model we are using. So this is one of the results about purity. And we see that in this picture, we have three phases. In between, we insert an ultra-slow phase, and we find efficient decoherence of an ultra-slow phase than in slow phase. And the other important result we got is we find that the transition between these phases really affect the final result of purity. So next step, we come to the real space entanglement proposed by Martin and Vanny, and we discussed the entanglement structure in ultra-slow. So It turns out that Storer and Altuve has the same mutual information and quantum discord and the entanglement structure because they are linked by one's duality. And we proved that every background linked by one's duality has the same entanglement structures. Finally, we also checked whether the transition between different phases does affect the mutual information, for example. Thank you.
Thank you. And Guillermo Martinez, come. Okay.
Hi everyone, I am Guillermo Martínez Somonte. I'm a PhD student in Instituto de Física de Cantabria in Spain, and I'm going to present very briefly my work on the primordial power spectrum reconstructions. So for this work, I employ a methodology of a Bayesian approach to freely place n nodes in the scale against the primordial power spectrum logarithmic plane. And in the right-hand side, you have a plot of an example of a configuration of 5 nodes. So we just sample the 2 pairs of coordinates for each node. And it's, you may note that in the case that if we sample just 2 nodes, this case will be totally equivalent to a power law. So what we do in the left-hand side plot, we reconstruct with just 2 nodes in the pink reconstruction, and also we reconstruct for 3, 4, 5 nodes up to 7, and we combine all the nodes with a Bayesian, combining the evidences of each configuration in order to generate a marginalized over the number of nodes spectrum, which I plot in the reconstruction in blue. So in that plot, you see an example in which we have an input feature in dash black, and we just see that our marginalized reconstruction is able to properly track this feature. So for our reconstructions, we apply a couple of tests. The first is a Bayes factor test, in which we compare the evidence of the power law case against the other evidences. And the other test is an hypothesis test that quantifies how the contours are separated. So in our first application, we did a forecast for JPass. In the right plot, we tried a feature of an oscillatory feature of 10% amplitude. And we just played with different observational specifications of JPass in order to see with which specification we have the most accurate reconstruction. So the Bayes factor points at a substantial detection, at a decisive detection of the feature. And we also played with the amplitude of this feature, and we were able to spot up to 2% amplitude features. So we have a paper in which we discuss very briefly the specifications that of JPass that are optimal for this. We need the most area possible and an intermediate receive mean as the optimal case. And now we are working with an application of BOS and eBOS that I will likely discuss with you in my poster. Thank you very much.
Good. Thais Miranda. There it is.
Thank you. Hi, I'm Thais Miranda, and I recently joined UNS. So this is an ongoing project that I started with Vincent Venan, and I know that bouncing cosmologies are not the main goal of this nice conference, but since we have so many experts in the stochastic formalism, I thought that I could get nice chats with by talking about this. So yes, we start from an effective Friedmann equation which accommodates a bounce. So you can see that when rho over rho critical is 1, then you have h equal to 0, and this represents the bounce, but you can also have a contracting universe and an expanding universe. And since this effective Friedman equation changed the time dependence near the bounce, our main question will be what is the role of quantum diffusion? And our approach is to implement the stochastic formalism directly in the phase space variables. And in this way, we have the evolution of the setup during the bounce, but also in the contracting phase, in the expanding phase. And I would like to say, as main result so far, we know that the effective index of the Mohanov-Sazak equation null, it will be relevant for the characterization of the quantum noise. So we are building a Langevin equation. And if you want to know more about this, please come to visit my poster. Thank you.
Next one is Ilya Misko.
Hello, everybody. So thank you very much to the organizer for giving me this chance, because despite I'm talking tomorrow about primordial black holes, I wanted to advertise this completely different work I've did recently. And I think it's a bit brave of me to talk about an alternative model to inflation in a place where really people are keen on inflation, but let's give it a go. So the idea of this work that we did was to investigate the possibility if we really need a scalar field to produce low roll inflation, or this is something that can be emerged from the physics that we already have. In particular, we looked to the idea of nonlinear electrodynamics, where we have a strong coupling between the electromagnetic field and gravity, because actually there is a strong, quite of a history about these models, from Born-Infeld theory, from string theory, and also there's been used a lot to remove the singularity from black hole physics. And, but it happens that in all the models proposed in the literature fails. So we wanted to ask ourselves why they failed, because it was not clear why. So we attacked the problem from a very general perspective. So we computed starting from the general action from a nonlinear coupling. You will see here the stress energy tensor in a perfect fluid approach, because we do this in a background calculation. So you can see here the density and the pressure written, and then we do the standard approximation that you do in this context, which is to have the electromagnetic field equal to 0, because the strong the interaction that the field has with the radiation basically allows you to screen the field. So you just have reduced yourself to a magnetic universe. And then you just go through the calculation. You write your Lagrangian, it would just have a kind of an equation of state like a perfect fluid. You compute your, you see that it works with an accelerated expansion. You make your slow roll parameters. And then in these particular models, what you have is that there is no Big Bang singularity. The singularity is pushed towards minus infinity. So the universe emerges for an infinite amount of time, and then at some point expand. And you want to, the constraints are that the slow roll parameter goes to 0 when the scale factor goes to 0. And then if you really solve the equation, actually you find the Lagrangian. It's a very simple one. It's a logarithmic form that you see, where basically you have 2 degrees of freedom in this Lagrangian. The beta is the nonlinear coupling, so it tells you the intensity, how the coupling between gravity and the electromagnetic field. And you have a free function, which is basically tells you how you go after inflation to your standard Maxwell limit. But apart from these 2 degrees of freedom, everything is given. And so the idea is that actually nonlinear electrodynamics are viable models. So the next step would be, and of course it's going to be challenging, you can do slow inflation, but can you really produce the power spectrum with this model? Well, that's another question for the future. Thank you very much.
Arnab Paul.
Hello, I am Arnab. I am a postdoc from IIT Madras. I thank the organizers for giving me the opportunity to present my work here. I shall be talking on origin of suppression in the power spectrum of primary gravitational waves at high frequencies, which is based on a work with Ali Prior, Professor Jeevan Martin, and Professor Sriram Kumar that we will put in archive this week. So I will start with the power spectrum. So as we all know, it goes as k cube into mod mu square, where mu is the Mukhanov-Sasaki variable, which follows the Mukhanov-Sasaki equation with the effective potential of A double prime by A. So if we start with the de Sitter inflation, and if we go directly into the radiation domination phase, then the effective potential looks like this, and the power spectrum has a k-square growth at small scales. By small scales, I mean the scales which were always sub-Hubble. They never went outside the Hubble radius. So as you can see that after this, in the small scales, it goes as k-square, and it is for a reheating temperature of 10 to the power 15 GeV. It actually goes through the bounds from cast, so it is observationally not allowed. And also for theoretical reasons, we know that we need to regularize the power spectrum for the primary gravitational waves. So one of the way to regularize it is the usual way to regularize is to do the adiabatic regularization. So adiabatic regularization is calculating the adiabatic power spectrum up to second order in adiabatic up to second adiabatic order, and subtracting it from the power spectrum that we calculated before. If we do that, then we can see that the k-square growth of the power spectrum at small scale is gone, and we get an oscillatory power spectrum at small scales. However, this is not enough. It can be shown that if we want a well-behaved two-point correlation functions, generic two-point correlation function at in real space, then we need to do something more than that. So this is actually smoothing the effective potential that I showed before. So here we have used a linear smoothing function, linear in eta actually. And if we do that and calculate the regularized power spectrum, we see that we get still the oscillation at small scales, but it is going as 1 over k. So we have a decaying oscillatory power spectrum at small scales. So this is the conclusion. So regularization is required from both observational and theoretical point of view, and we need adiabatic regularization for that. However, smoothing is also required to get a well-behaved two-point functions in real space. So thank you. If you are interested in it, so you can come to my postdoc.
Next person is Alitza Rogel. Yeah. Yes.
Hi, thank you. Hi, I am Alitza Rogel. I'm a final year PhD student at the University of Bern, and I want to talk to you about the stochastic simulation of reheating. So just as a quick reminder, reheating, this is this bridge between inflation and radiation domination. And now during inflation, one of the key things that happens are quantum fluctuations, which source scalar perturbations. And in our project, we then evolve this scalar perturbation through the reheating period until radiation domination. The degrees of freedom that we used were the perturbations of the inflaton field, the perturbations of the plasma, in particular that of the temperature and phore velocity, and the perturbations of the metric tensor. Now, the big picture here is that at the beginning, inflaton has the dominant component in the energy density, but then it is slowly transferring it to the plasma through this dissipative term here, until at some point then plasma has the dominant component of the energy density, and then we talk about radiation domination. Now, because this process happens smoothly, this is called smooth reheating. So what do we do in practice? We derive model-agnostic stochastic evolution equations for the power spectrum, and then we solve them numerically. And one particular example of our solutions is the standard model with QCD axion. And now just a few details. So in our work, we insist on gauge invariance in our equations and in our solutions. We also do not need a slow, or we do not rely on the slow roll approximations with our equations. And also, we do not need to assume in advance whether inflaton equilibrates or not, but this is rather a question that's answered dynamically. We also make sure to have correct quantum and classical limits, and yeah, a few more things. And if you're interested, please come talk to me downstairs. Thank you.
The next person is Haridev. I don't have the first name. Yes. Yes.
Hi all, and thank you for the opportunity to discuss our work in this platform. And as you can see from the title, in this work we computed the 4-point autocorrelation function of U1 gauge field during the time of inflation. And this is a collaborative work which I did with P. Jishnu Sai and Professor Rajiv Kumar Jain. Introduction of gauge field in the inflationary scenario is motivated strongly by the strong observational indication of presence of coherent weak magnetic field in the intergalactic spaces, which you already heard from the talk from Professor Sriram Kumar. And in our work, we are working with the action as shown here, where this look almost like the standard electromagnetic action, except for the presence of lambda of phi coupling. This coupling is called the diatonic coupling, and this actually breaks the conformal symmetry in the theory, which is required for the amplification of U1 gauge field during the time of inflation. And in the gravitational sector, I will be working in the co-moving gauge, and using the standard ADM decomposition, you can construct the interaction Hamiltonian for the scalar exchange as shown here. I will be showing the results mostly for the scalar exchange only, and at the end I will show also the results for the, just the outline the results for the tensor exchanges. And once you have the interacting Hamiltonian, you can use the standard in formalisms to compute the trispectrum or the any correlation functions. And these will be the diagrams which we are interested in, and specifically first two diagrams. And using the cosmological in formalism and the cosmological diagrammatic rules, we computed the trispectrum for the magnetic field, especially for the contracted version B dot B, and this will be the result. And as already heard from in these discussions, these trispectrums can be decomposed into Q and I, where Q contains the information about the polarizations and I will be just the nested time integral which you have to compute. And in this special case of contracted version, the Q's will be given by single functions of cos thetas, and theta 1, 2 will be the angle between the external momentas. And in the momentum space, this will form a closed quadrilateral, and in general, this won't be a planar quadrilateral. You will have three-dimensional configurations, and we will be studying the different configurations for this quadrilateral. First, the equisided configuration, which you can study just using two characteristic scale in the theory, and the results will be as shown, and all the important features will be gone into these functions called f, which you can plot for different values of phi, and specifically for phi equal to 0, we are getting a monotonically increasing function starting from a non-zero value, where ki, which is the exchange moment, will be 0, and which maximized at the exchange moment is 2k, which is the flattened limit. So the trispectrum signal will be maximized at the flattened limit. And next, the ki tends to 0 is another interesting limit, which is the countercollinear limit. And in this limit, we are able to derive a new consistency relation in the theory, which is similar to that of the standard Tsuyama-Yamaguchi relations. And this actually relates the nonlinearity parameters in the trispectrum to that of the bispectrum. And all these similar analysis you can do for the tensor exchanges also, which we did in our analysis. And the major difference will be, now the exchange particle will be spin 2 particles, and they have their own helicity. Their signals will be suppressed due to the scalar tensor ratio, which is small. However, there will be specific angular dependence in the theory, and this can be also be studied in the different limits and countercollinear limits and equisided configurations. And this distinct angular dependence can be observed in the future observation, more precise observations. And that concludes my talk. Thank you. And if you are interested, please visit my poster downstairs. Thank you.
Thank you very much for actually all the presenters to be exactly on time. So now we have Jose Jaime Tenente. Here it is. Thank you.
Well, thanks. So I'm Jose. I'm from the University of Coimbra, and I'm presenting here a work in progress that I'm doing in collaboration with Ricardo Ferreira and Alessio Notari. So essentially what we are considering here is an action with an axial coupling between a massive abelian gauge field, which is something you would expect from thermalization or a Stuckelberg mechanism, and a pseudo-scalar and action-like field which results in a tachyonic enhancement of the gauge transverse modes during inflation. And this back reacts on the evolution of the scalar field, as you can see here in the case of the homogeneous evolution. The A dot B would correspond to the back reaction term on the homogeneous level. And as you see, it acts as an additional source of dissipation. In addition to that, we also have back reaction on the Hubble expansion rate because of the presence of this co-moving energy density of the gauge fields. And we can provide analytical expressions for these two back reaction terms if we assume a regime of weak back reaction, meaning that the tachyonic enhancement of the gauge transverse fields does not back react on the evolution of the scalar field. We assume that there is no back reaction at that level, and assuming that the scalar field follows a standard slow roll evolution, we can compute the E dot B and the rho, which is what we do here. The interesting result is for the very heavy gauge fields, which, as you can see here, we have written in terms of the expressions for the massless case. And in that case, you can see that in for both expressions, the dependence of the mass is the same, meaning that the ratio is essentially the same as in the case of the massless case, which is inversely proportional to the parameter that causes the tachyonic enhancement of the gauge transverse modes. Using those expressions, we can determine the onset of moderate and strong back reaction, which is given by these two equalities here, respectively. And if we do so for the different values of the mass, we can see that as we increase the mass, this relaxes the constraints on the slope of the potential energy density that we get if we solve those equations, which are a sort of Lambert equations. So by solving those, we get constraints, and those are relaxes for larger values of the mass. In addition to that, we also have back reaction at the level of the perturbations. This is because of the presence of many inverse decays processes, which give a new contribution to the power spectrum. This is what I call here the PID. You can see down here the expression in the case of the Sitter expansion, which is 3 integrals. The 2 first integrals cannot be done analytically, but the last one, in the case of light and massless gauge fields, you can solve it analytically. In the case of massive gauge fields, you have to solve it numerically. It's a bit more complicated, but it can be simplified quite a bit, and it can be done numerically. So by doing so, we have plotted here for different values of the mass, and also this xi that you see here, which is the responsible for the tachyonic enhancement of the gauge fields. You can see that for different values here, the values for which there is an onset of the moderate and strong back reaction at the level of the perturbations, which is the solid curve, also on the homogeneous evolution of the field, which is the dash curve, and also the Hubble expansion rate, which is the dotted one. So now what we are doing is just dealing with the numerical simulation. And of course, if you have more questions, please feel free to come. I believe that the food downstairs is even much tastier than the one you have here at the entrance. And it's much warmer, actually, so please.
Okay.
Thanks. Now we have Olive Weissenen.
Okay, can you hear me? Okay, good. My name is Olli Väisänen. I'm a PhD student at University of Jyväskylä, working with Kimmo Kainula and Sami Nurmi. And the topic of my research is out of equilibrium quantum field theory. So in addition to inflation, of course, out of equilibrium quantum fields are important in many aspects of early universe, like baryogenesis and so on. And our application in that sense is gravitational production of scalar dark matter with non-minimal coupling to gravity and also self-interactions. So the physical picture is relatively simple. So as slow roll ends, the inflaton begins to roll at the bottom of its potential, and each time the curvature rolls into negative, we get a burst of so-called tachyonic particle production. And on the right, you can see in here the resulting power spectrum, its time evolution. But it turns out that in this application, the production is actually dominated by nonlinear effects like nonlinear parametric resonance at the end. So the question here is, how do you simulate a quantum field that is fundamentally nonlinear? And our approach is 2PI formalism, which essentially allows you to get evolution equations for the fully resummed two-point correlation function. The problem there is that these equations are extremely computationally intensive. So our work is to formulate these equations basically as a generalized Boltzmann kinematic function plus explicit quantum corrections. And these equations we can then solve more numerically easily using standard methods from kinetic theory. And to end, where would this kind of formalism be useful to you maybe is if you want to deal with non-perturbative quantum effects. For example, if you want to look for thermalization of fields, and also this same kind of construction will work for both scalars and fermions, for example, so you could have interacting scalars and fermions. Thank you.
Here it is. Okay, thank you. Okay, hello everyone. So my name is Simeon Vareille. I'm a third and final year PhD student at the Centre de Physique Théorique at Marseille. And in my poster, I'm gonna briefly present a project that I have undertaken with in collaboration with my supervisor, which is Federico Piazza, which is about describing cosmological bouncing behavior already at the level of a radiation-dominated universe. So the idea is to base the ground equation on the Wheeler-DeWitt constraint, which is the fact that the Hamiltonian of the theories vanishes on shell of the Laps constraint due to the theory's invariance under time reparameterization, and to add to the dominating physics a test field which will act as a clock. So to think of adding a clock as a new degree of freedom in the picture, and that turns the Wheeler-DeWitt constraint as a Schrödinger equation, from which we can then apply this to a radiation fluid model, which has the kinetic term and a potential term. And already at the semi-classical level, if one uses a semi-classical WKB ansatz to this equation, one recover standard classical behavior of the profile of the scale factor as a function of time, and one can also numerically evolve this Schrödinger equation, which is given on top of here. So the kinetic term and potential terms, and this at the quantum level is regular. So this Hamiltonian admits bound states because the potential is identical to which of an S wave scattering off a central potential, which is of this type, minus r to the minus 2/3. And the problem we consider is the one of preparing initial semi-classical states so far away from the origin, and to impose boundary conditions at the origin, and to evolve those wave packets through the Schrödinger evolution. And with that, when we plot the expectation value of the scale factor as a function of time, the scale factor follows the classical trajectory at early times before departing from singularity collapse as it approaches the origin. And I discuss whether some aspects of inflation could already be captured by a bouncing behavior, because this already provides an expansion epoch, and also an epoch where the degrees of freedom are homogenized, which is a requirement of inflation. So yeah, if you are interested in knowing more about that, please reach out. I'm happy to talk about it more. Yeah.
Next is Ao Wang.
Hello everyone, I'm Ao. I'm glad to be here to share my recent project. this project starts with a question that's what are we measuring if there is a gravitational wave arose from second order effects. For example, the gravitational wave induced by density perturbation is a type of second order gravitational wave, and it could be detected in future experiments or even be relevant in current pulsar timing array data. So the question appears because in this case, the transverse traceless part of metric perturbation, which we usually use as a gravitational wave observer, and no longer gauge invariance. So in our work, we construct observable directly from what we are measuring. Specifically, we consider idealized setup in an expanding universe. We have two observers, and they are exchanging light signal with each other. And we know that the proper time when the second observer receives the light should be independent of the coordinate we choose. But if we want to understand how the received proper time depends on the metric perturbation, we should solve it perturbatively. And at the first order, we decompose the contribution according to their dependency on the propagation direction. And from the form of the equation, we can notice that there are two terms are related to the motion of observer, and the other two terms is related to the propagation effect induced by the metric perturbation. And these two corresponds to the gravitational wave effect and the Shapiro time delay. And we noticed that the gravitational wave effect has a quadruple dependency on the direction. And then we generalize our result to second order and focus on the quadruple effects. And we noticed that the propagation effect is related to the TT component in Newton gauge. And the other term is related to the first order perturbation to the observer position and velocity. And furthermore, we show that such a quadruple dependency on the direction can lead to the Healy-Dance curve, which is commonly used in pulsar timing array to distinguish gravitational wave from noise. So that's my project, and thank you for your attention, and welcome to see you in my post, by my post.
Thank you. Next we have Zenteno. Yeah, right. Cristobal Zenteno.
Hey everyone, I'm just here to advertise my poster and then we can chat a lot, like lengthy along it. So in my poster, in my work, I work along this chromonatural inflation system, which is just simple as an axion plus an SU2 gauge field. And this kind of system has like many good features, really interesting. Some of them are like the chiral tensor modes and so on, but this has a nice challenge or issue is that like it can be proved that almost all chromonatural setup that is consistent with CMB constraints is almost inevitable to reach to a regime where the tensor back reaction has to be taken into account. This is really simple how to explain it. It's like in this map where I can show you that the constraint, like the parameter space constraint between the G value, the gauge field strength, and the MQ, which is related to the gauge field vacuum expectation value. This evolves, and then even if you start in a CMB really weak back reaction regime, you will evolve up to hit the strong back reaction regime. So I can talk to you like what does it mean with consistent with CMB constraints, but now in this work we solved the evolution including the tensor back reaction. And we identify a really interesting evolution between
something that we call weak back reaction regime, up to a regime that was already illustrated by Oksana in her work, in her talk, the strong back reaction regime, that is described by a really interesting new attractor. And in between, we have like two interfaces that we can discuss after. And the really interesting part about like this phenomena of the transition between weak and strong back reaction regime is that, for example, it generated really interesting features in the gravitational wave spectrum. We have 3 peaks, or 2 and 1 remnant peak. One came from the direct tensor modes. A second peak can be generated by scalar-induced gravitational waves. And then we have a remnant from the other chirality. So my objective of this talk is just to give you some questions that we can discuss along my poster. For example, what about the chirality of the signal? What about the tachyonic instability on the scalar sector? What is the scalar power spectrum? I have the nice plot in my poster. What is the potential election? You can see in the title, we say pure chromonatural. Where does the pure came from? And what is the parameter space regime? We can talk about it along my poster. Thank you very much.
Okay, next one is Yisung. So now we have Yisung Chang.
Thank you. Good afternoon. My name is Yisong, and this project is about the physics of inflation trajectories on the landscape, which is under instructions by Xingang Chen from Harvard, and Luca from ENS, and Zhongzhi, who is my supervisor. Well, sorry. This work motivates from the so-called eta problem, which states that the slower inflation requires the value of eta v of the inflation potential to be a small number. But the natural value of eta v is of order 1, both from the EFT or the string theoretic perspective. In this setup, in this work, we studied the inflation happened on a multidimensional inflationary landscape, which satisfies the constraint given by eta v in a statistical manner with a correctly defined eta v on a multidimensional case. And the inflation is happened due to the occasional cancellation of eta v on the landscape, as illustrated in this figure. Technically, we build up the field potential in terms of random functions characterized by a correlation length called xi. The quantity xi essentially controls the value of eta v on the landscape and can be chosen so that the eta v constraint is satisfied. On such a realization of a landscape, we can solve the equation of motion of a large number of randomly chosen initial conditions and collected all the solutions that falling into the true vacuum. And this procedure can be repeated many times for different realizations of the landscape. And the most obvious question is whether the inflation can last long enough on such a landscape. To have a feeling of the answer, I show here several distributions of E40 numbers of trajectories on several different realizations of the landscape. And as you can see, in most of the realizations, they don't possess a trajectory with a long enough E40 number, but there are a few lucky ones, such as the one at the lower left. And moreover, if we merge these histograms of different realizations to a single one, you will find that the distribution of the E40 number of a trajectory takes the form of a log normal profile. And the long-lasting trajectory appears as the rightmost tail of the distribution. And such kind of a long-lasting trajectories have many, many interesting features, interesting properties. The first is we find that most trajectories are multi-field, meaning that their trajectories in the field space is a curve. And secondly, we find that around half of the trajectories are multi-stage, meaning that they have more than one slower phases during the whole history of inflation. And among those multi-stage trajectories, there are a few of them appear to have some oscillatory feature, as you can see, as can be seen in the power spectrum and the trajectory. And such kind of a feature are more frequent on landscapes with larger values of eta. All in all, the phenomenology is quite abundant, and I can't give a very comprehensive introduction here, but I'm it's welcome to contact with me afterwards. Thank you for listening.
Now we have the last in-person presentation, because we'll have one remote presentation. Zhao.
Hi everyone, I'm Yun He from undergraduate student from Southern University of Science and Technology, and my poster is based on this work and in collaboration with Sebastian and Junjie. And there's a well-known theorem about the geodesic path completeness in general relativity given by Bode-Guth and Vilenkin. And they define a generalized Hubble parameter, which is respect to an observable, which describes the separation of some test particles pass through the word line of the observable. And the BGA theorem gives a criteria such that if the time average along the observable of the generalized Hubble parameter greater than 0, then the space-time is path incomplete. So we apply this BGA theorem into FRW space-time, and we know the Hubble today is greater than 0, and we always can notice that in FLRW space-time, the generalized Hubble parameter is just a Hubble parameter we know. And if we want our FLRW space-time be path complete, it should exist a bounce. But in 2023, as Essen and Lesniewski gives a counterexample of this theorem, they point out the BGA theorem contains the subtle loophole. So our work is try to find a way to solve this loophole of BGA theorem, and we change the criteria of the path incompleteness into H average greater than an arbitrary small number delta rather than 0. And in this case, we open a window for so-called emergent universe. That means the scalar factor equal to a positive constant as the cosmic time goes to minus infinity. And this is an example for the emergent universe which has no bounds, but it is path complete. So we also have an result that said if we want FLRW space-time to be path complete, and we also assume the Hubble today greater than 0, we find there must exist a phase of the accelerated expansion. This is our main result. And if you want to know more detail, come to my poster. Thank you.
Thank you. Now we have one last poster presentation, I believe, online by Suresh Kumar. Yes, so you're plugging here.
Hi everyone, this is Sudesh Kumar. So this work has been done with my thesis supervisor, Professor Saurabh Bhattacharya. And So brief motivation of my work is, so we want to study the effect of the Yukawa coupling during the inflationary scenario. So what we consider in this work is that there is a coupling between Yukawa and scalar field. And scalar field here is the spectator scalar field, and the method that we are using here is stochastic spectral expansion method to calculate the various correlation function, including the 3-point correlation function. So we start with the de Sitter space-time, and the matter action reads age. So we consider the harmonic field coupled to scalar field, spectator field, that is here. And with that there is a coupling, that is Yukawa coupling. And so we construct the effective one-loop effective potential at first order, at a leading order, and we get the total effective potential and a schematic of and plot of this effective potential with the scalar potential, that is alpha pi to the absolute pi to the p, where p is more than 4 and alpha is more than 0. So this is the effective potential for various g values. So next we consider compute the various correlation function using the stochastic spectral expansion method. So we have power spectrum and the spectral index, and our main focus is on the density fluctuation, where the effective potential dominates, and we compute other correlation function, that is a 3-point correlation function, using the 1-point particle distribution function. And in the momentum space, we compute the bispectrum, and in the squeeze limit, we finally get the nonlinearity parameter, that is FNL local, in the local regime, and where S is the space shape function, that is in the local space. So finally, there are some numerical results that we find. So we see that at the large G values, spectral index is increases, and at the large G value, power spectrum decreases. So we see that effect of Yukawa coupling at a large G is dominating, but at a small scale, small value of the G, it is not dominating. So for the effect of Yukawa coupling, we have to choose the large G value. And in the case of the non-Gaussianity for the local, we see that it is going out of the bound for large G values. So we have computed all the results in the Planck limit. So for all the constraint using the Planck data. So this is a summary, and so we see that we have computed various correlation function, and we want to see the effect of the Yukawa coupling on various correlation function and on the non-Gaussianity. So for large G, we see that some effect on all the cosmological parameters. Thank you very much.
Okay, so now maybe a final round of applause for all the presenters of this second session.